In the previous video, we described central tendency, which are one set of descriptive statistics that are used to describe the center point of a distribution. In this video, we're going to describe measures of dispersion, which is a second set of descriptive statistics which describe the spread of the distribution. And in this video, we're going to cover 10 different measures of dispersion: population and sample variance, population and sample standard deviation, the average absolute deviation, the median absolute deviation, the range, skewness, kurtosis, and standard error of the mean. Now, it's important to understand all of these because some are foundational for some of the statistical processes we're going to conduct later. But for reporting purposes, so when we report our descriptive statistics, most commonly we're going to be using sample variance, sample standard deviation, range, skewness, and kurtosis. So variance is a measure of how far the observations in a distribution are away from their mean. And thinking about why variance is an important measure to report is that if we have two values in a distribution, 4 and 2 for example, the mean of 4 and 2 is the value of 3. Now in another distribution, let's say we have two values, 3 and 3. Now the mean of that distribution is also 3. And so if we report just the mean, we don't have an understanding of what the shape of the distribution looks like. The values of 4 and 2 are going to have a higher variance level than the values of 3 and 3, simply because the values of 4 and 2 have an overall greater distance away from the mean of 3 than the values of 3 and 3. Now, in the work that we do, we generally work with a sample, and so we more commonly report sample variance. Population variance is more of a theoretical concept, and it represents all of the observations of a particular population distribution that we might be sampling. Now, there isn't a function in R to calculate population variance, so we're going to use the package sjstats. I already have it installed on my computer, so I'm simply going to load it using the library function, and we're going to use the var_pop function. And let's say we want to calculate the population variance of our music perception scores variable. The population variance for our music perception scores variable is 0.03. Now, sample variance is similar to population variance, but it makes an adjustment for the unknown population parameter. And we can calculate sample variance by using the var function. So the sample variance of our music perception scores distribution is 0.03. So we see here that it's very close to the population variance. So here we see just a slight correction, but if we're rounding to 2 decimal points, the difference between the two statistics is negligible. Now, similar to variance, we also have a population standard deviation and a sample standard deviation. Now, standard deviation is also a measure of the dispersion of all the observations within our variable. However, the difference between standard deviation and variance is that standard deviation is standardized. In other words, standard deviation is reported in a standardized unit of measure, where variance is reported in the units of measure of the variable that we're looking at. And we're going to talk a little bit more about standardization later. So again, in R, we do not have a function to calculate population standard deviation because it's really not reported often. So again, we're going to use the sjstats package, and we're going to use the sd_pop function from that package. Again, we'll pass in our music perception scores variable. And we see that the population standard deviation is 0.17. Now, to calculate the sample standard deviation, which we'll most commonly report along with the mean, we can use the SD function. Again, if we take a look at our music perception scores variable, we see that the sample standard deviation is 0.17. Now, the next measure of dispersion we can look at is the average absolute deviation, which is sometimes referred to as the mean absolute deviation. And it's the average of the distances between each of the values in the distribution and the mean of the distribution. Now, in order to calculate the average absolute deviation of a distribution, we're going to use the LSR package to do that. Again, I have it installed on my computer, so I'm simply going to load it using the library function. And then here we're going to use the AAD function. And then we'll pass in our music perception scores variable. And so the average absolute deviation for our music perception scores variable is 0.14. Now, the median absolute deviation is another average of absolute deviations for all of the values from the mean in the distribution. However, here we're going to be using the median instead of the mean, which we used for the average absolute deviation. So in order to calculate the median absolute deviation, we can use the MAD function. And we'll pass in our music perception scores variable. And the median absolute deviation of our music perception scores variable is 0.16. The next measure of dispersion that we're going to calculate is the range, which is also sometimes referred to as the spread of the distribution. And it describes the distance between the minimum value of the distribution and the maximum value of the distribution. And we can calculate the range by using the range function. And so the minimum of our music perception scores variable is negative 0.67, and the maximum value of our distribution is 0.53. Now the output of the range function provides for us the minimum and the maximum value. Another important way we can report the range is with one value, and that's the distance between those values. So we could simply subtract 0.53 and negative 0.67. However, it's better to use a function to do that. And so we're going to use the desk tools package to do that. I already have it installed on my computer, so I'll simply load it using the library function. And here we're going to use the range function from the package. Note that the function uses a capital R. And again, we'll pass in our music perception scores variable. And so here we see that the range is 1.2, and it also provides the minimum value and the maximum value of the distribution, sometimes referred to as the upper bound and the lower bound. Now the skewness of a distribution describes the symmetry of the distribution. And the expected value of skewness for a normal distribution is 0. The closer the value is to 0, the more representative it is of a normal distribution. A negative value indicates that the data are left skewed or negative skewed, and a positive value indicates that the data are right skewed or positive skewed. Now in order to calculate the skewness of our distribution, we're going to use the psych package. I already have it installed, so I'm simply going to use the library function. And then here we're going to use the skew function. Note that there's also a skew function from the desk tools package that we use, but here we'll use the psych package. And we'll pass in our music perception scores variable. And we see that the skewness of our music perception scores variable is 0.14, suggesting that the distribution is slightly right skewed, sometimes referred to as positively skewed. Now, kurtosis is another measure of symmetry of the distribution, but more specifically, it's an indicator of how heavy or light-tailed the distribution is. And there are two different values of kurtosis that we can use, kurtosis proper and excess kurtosis. And in research papers, it's not commonly identified what specific value of kurtosis is used. So here, it is important to identify which one is being reported. Now, the expected value of kurtosis proper for a normal distribution is 3. The expected value of excess kurtosis for a normal distribution is equal to the value of 0. Now, in order to report excess kurtosis, we're again going to use the psych package that we just loaded. And here we're going to be using the kurtosis function. And we'll pass in our music perception scores variable. And the excess kurtosis value of our music perception scores variable is 0.92. Now, in order to calculate kurtosis proper, we're going to use the moments package. I have it installed. I'm just going to load it using the library function. And then here, we're going to use the kurtosis function. We'll pass in our music perception scores variable. And the kurtosis proper value for our music perception scores variable is 3.97. Now, we can describe kurtosis in one of three ways. A kurtosis proper value of 3, or an excess kurtosis value of 0, is referred to as mesokurtic. A measure that is positive, like we see here, is referred to as leptokurtic, because the word lepto, meaning slender, demonstrates longer tails than the expected normal distribution. And a measure that's negative is referred to as pleitokurtic. And pleity, which means broad, demonstrates shorter tails than the expected normal distribution. And we're going to see more of what that looks like when we visualize the data in future videos. Now next is the standard error of the mean, or sometimes just more simply referred to as the standard error, and it's a precision measure of how representative the sample mean is of the population mean. And we're going to explore this in much more detail when we talk about simple linear regression. And in order to calculate the standard error of the mean, we're going to use the mean SE function from the desk tools package. We already have desk tools loaded, so we don't need to load it again. Note here that it's coming from the desk tools package. And we'll pass in our music perception scores variable. So the standard error of the mean is 0.01.